diagram again. So this is orthogonal cutting. Orthogonal cutting also means that the cutting speed is coming out, and the edge is perpendicular to the cutting speed. Right? And we have wriggle phase, this is the wriggle phase, and wriggle angle, and this is the flank angle when the flank wear, this is a flank phase. And usually here is as the time goes, and the tool will be worn out. How this guy will be worn out, and the several crater, we might have craters on wriggle phase, and we will have the flank wear on this surface. So this is uncovered chip thickness. So this is a chip thickness, and also so here is the angle. What do we call this angle, guys? Here, what do we call? Yeah, here. This is shear angle. Okay, shear angle is very important one. So and we will use shear angle to calculate the cutting forces and energy consumption, a lot of those things we need to use shear angle. By the way, these equations those equations are empirical equations. Sometimes it is not accurate, but this can give us a sketchy idea. And based on this is cutting processes to material, to geometry along the workpiece material, and we can have a sketchy idea on what kind of cutting force we will get, what kind of energy consumption we will have. So this is a chip formation, and so we have a shear angle here. Luckily, we have this triangle, and this triangle can be solved and using the trigonometry knowledge we have learned. That is called sine theorem, right? So sine theorem means that the magnitude of this side divided by sine of this corresponding angle equals the magnitude of this one divided by this guy's corresponding angle, sine of this corresponding angle, and so on for this one divided by sine of this one. So this is to give us the relationship between the V is the cutting speed, and the VC is chip velocity, chip speed along the rig face, and also here is the shear speed, and shear speed is on the shear plane. So this is sine theorem give us this relationship. Okay? So this is a very important one. So the forces in the orthogonal cutting. So why we have we need to have forces in the orthogonal cutting? Because we want to remove part of the materials from the body of the raw material, right? So that means a crack. If you want to crack anything, then you must give some work, energy in terms of from the perspective of energy. You need to provide some energy, and in terms of force, and you need to apply the force, right, to do some work. So knowledge of cutting forces and power requirements in machining operation is essential for the following reasons. Why this is very important. The first one, the power requirements. If you want to produce, to generate this the final products, and for the very hard material, okay? And so you need to know the power requirements. So if this material is very tall, maybe in our machine shop, the power cannot satisfy this requirement. If you do it, and immediately the fuse will be blown up. Right? So this is, you need to know the power requirements. The power requirements must be determined so that the machine tool of the suitable capacity can be designed and also selected for a particular application. So before you do anything, and you need to, as an engineer, you need to use your hands to do some kind of calculations and to estimate what kind of power requirements I will need for this particular application. Okay, and then the data on cutting forces are necessary for the proper design of machine tools. Whenever you see the machine tools is the whole equipment. For the lathe, the whole equipment is called machine tool. For the milling tool, for the milling machine, the whole thing is called machine tool. Whenever you see machine tool, that is not the tool itself, but the whole equipment. Does that sound right? So this is the machine tool. This is what the machine tools mean. So that they are sufficiently stable. They must be stable enough, thus avoiding excessive distortion of the machine components and vibration and chatter and maintaining desired dimensional accuracy. So the carding force, because we have carding force, right? Whenever you want to remove some layers from the raw material, you need to provide some force. However, if the system is not stable enough, what will happen? So this system will be vibrating. If this guy vibrates, right? Because your workpiece is mounted on the machine tool, if this guy vibrates, your tool, even though your tool is very stable, it can adversely affect the dimensional accuracy, right? Is that understandable? So the stability is very, very important. So now the people want to use industrial robots and to want to replace the people and to do some very, very dangerous work for machining. But because you know Joyce, right? Have you ever used the industrial robot? So we have industrial robots just like our own. We have several joints. Because the existence of joints, the stiffness of industrial robots is not stable enough. So that's the reason now this is a research topic on how to enhance the stiffness of the industrial robots. So we can ask these guys to do something good for us. But now this is a metal block. This is the bottleneck, or this is the industrial robots application in the manufacturing. So third one, the workpiece must be able to withstand the cutting force without excessive distortion in order to maintain the dimensional tolerance. As I said, you must put the force there on the tool or on the workpiece. If this workpiece cannot withstand this required cutting force, this guy itself will be distorted right before you can remove some layers off. Right. So this is what you need to do as a mechanical engineer, as a manufacturing engineer, and whenever you have some new materials and the new tools, and you can use your hands to do some kind of calculation and to give an estimate about your power requirement, the cutting forces, all these things, even though it's not very accurate, right? But this is a sketchy idea, and we provide insightful suggestions. Any questions regarding this slide? Now we are focusing on orthogonal cutting, but actually, in reality, and most of the cuttings are not orthogonal cutting. Orthogonal cutting is idealized case scenario. So this is cutting force, and so we have this picture, but we did not talk about here, right? So this is the orthogonal cutting. So we have this chip, this workpiece, and this is our tool. The tool is moving this way. Okay. In this case, we just think the workpiece is stationary. Workpiece remains stationary, and the tool is moving. It does not matter. For the research, when we do the modeling, we can say this guy remains stationary, but this one is moving in that way. As long as we can accomplish this relative motion, that will be okay. You agree? Okay, great. So for this case, we will have this is Fn on this shear phase, and we will have normal force. Fn is a normal force, and Fs is a shear force. If you want to remove this chip, remove this layer from the body of the raw material, and you have got to generate, apply this Fn, this Fs. Right? So this Fn, this Fs actually is a reaction force from the workpiece because you apply the load. Based on Newton's third law, if you put apply some load somewhere, and so you will get the same amount of force. Is that correct? So actually, when we talk about the cutting force, and the actual cutting force actually is the reaction force of the force, and you apply it to the system. Right? the reaction force, that's the reaction force. Reaction force is what kind of forces the system give you because you apply load onto the system. So be very, very careful. So here, so this is our resultant force. This is resultant force. Resultant force is we just say because F1 and Fs they are orthogonal. So look at this red triangle, and this R resistance. And then, so this is R resistance, okay? So this is R resistance, but we want to decompose this R resistance in another two directions. One is horizontal, one is vertical. So, and then we will have FC, this FC is a carrying force, and this FT, what is FT? What does the T stand for? Thrust. Thrust means vertical to the carrying direction. So the thrust, the FT means the thrust force. Okay? FC is a carrying force. Carrying force is the force that is in the direction of the carrying direction. In the direction of carrying. So here, so this is R, FT, FC. So here is a phi. And so this is a beta. We call this a beta. This is F and N. Okay? You can see. And this R can be decomposed by two ways. One is F and N, right? Another one is horizontal and vertical. It's the same thing, because this one is a right angle, this one is a right angle also, right? The same vector, you can decompose this guy into in two ways, in multiple ways, not just two ways, as long as in each of these two ways, the two directions are orthogonal. Right? So you can see my R is resultant force of F and N, but here to calculate the direction, the force in the horizontal direction, and also the force in the vertical direction, I decompose this R using this triangle, this one. So based on this triangle, we can see FC, so as FD transpose, this FC, okay? FC is equals this R, this hypotenuse, multiplied by cosine of this beta minus alpha, because the whole thing here is beta. And how to calculate the beta? And beta determines the relationship between F and N. So this is R cosine beta minus alpha, and then we can have this is sin phi cosine phi plus. This is a friction coefficient. And friction coefficient equals tangent beta equals F divided by the normal. This is N. Right? So this is F. This is F, and this N. So it equals Ft. Right? So this is Ft plus Fc tangent alpha. This is alpha is a right angle. So this is numerator equals Fc minus Ft tangent alpha. So here is this is a tangent beta. This is a tangent beta. Tangent beta can be obtained using Ft and Fc. And when we express this beta mu using Ft and Fc, the reason is that when we use the dynamometer to record this carrying force, the dynamometer usually is mounted such that, and we will get the carrying force and the stress force. You know dynamometer, right? Dynamometer. Dynamometer is used to measure the carrying forces. Write down dynamometer. DYNA, dynamometer, dynamometer. The way we express mu in terms of Ft and Fc, because we can use dynamometer to directly record Ft and Fc. On the contrary, these F and N, they are not directly recorded, right? Even though when I talk about this figure, I say this F and R. F and N, they are not directly calculated, not directly recorded. FT and FC, they are directly calculated. So this is FC equals R cosine beta minus this is minus this alpha. Alpha is a rectangle. Alpha is a rectangle. The T0 is a uncut. This is the uncut chip thickness. So we talk about this current data. Okay, so current data. This is empirical curves. So this is the table, the data on orthogonal carding of 4130 still. So this is empirical carding, as I said. And based on different alpha is a rectangle, okay? The rectangle, how sharp your tool is. And phi, the phi is a shear angle. Phi is a shear angle. This is the mu, and this is a beta. Right? So this is a beta. FC and LT, and also this is UT, and UT is under the specific under it. So this W is the width. W is the width, and T0 is the uncolored chip thickness. W is the width of your workpiece. The width. Here is your width. Right? W is the width from here to here of your workpiece. So this is a beta, the mu, this is US, the 300 for shear, and UF is 300 for friction. So this is a percentage. So the stress force, this is the stress force based on the feed, different feed, and this is the stress force. The stress force as a function of rectangle, different rectangle you can see, for different angle, they have different curves. And the feed in orthogonal carding of this is AISI 1112 color road steel. Note that at a high rectangle, if the rectangle is high, it means that the tool is sharper, right? The higher the rectangle, the tool is sharper. Note that at a high rectangle, the thrust force is negative. And thrust force negative. A negative thrust force has important implications in the design of machine tools and in controlling the stability of carding of the carding process. Questions so far? Any question? Okay. So this is data on orthogonal carding 9441. So alpha, different alpha, plus 10, minus 10, and velocity, phi is gamma, mu, beta. This is FC, FT, UT. The total UT is the total stream energy. Okay. Specific energy. And US is the shear specific energy. UF is the friction specific energy. The tool here, and we use the semantics as a product. The shear force and normal force. We have shear force and we have normal force. These two guys are orthogonal to each other. So as a function of the area of the shear plane, the area of the shear plane equals length of the shear plane and the width of your piece, right? Okay. So this is the shear force, Fs, shear force. This one is the area of the shear plane and the rectangle for also the rectangle, 20 degree to 40 degree for this 85 to 15 press. Note that the stress here in the shear plane is constant, regardless of magnitude of normal stress. So indicating that normal stress has no effect on the shear flow stress of the material, of this material. questions so far? So here is the shear stress, is the shear force, okay? And this is shear stress. And shear stress is this one. This is the slope is constant. It means that the normal stress has no effect on the shear flow for this material. The shear force and the shear stress, you need to be very, very careful. They are different, right? One is the total force, another one is the force per unit area. So here is AS and also this F. This is a normal force. As a function of the shear plane. So we have different alpha here. Also, you can see for different alpha, the shear also we have the sigma is constant. This is straight line. So there are some observations. So the shear stress on the shear plane is independent of the rectangle. Is independent of the rectangle. The shear stress on the shear plane. The normal stress on the shear plane decreases and with increasing a rectangle. Okay. So the normal stress in the shear plane, has no effect on the magnitude of the shear stress, and a phenomenon that has also been verified by other mechanical tests. However, normal stress is a normal stress. I'm talking about stress, not force. Normal stress strongly influences the magnitude of the allowable shear strain in the shear zone before fracture. So this is normal stress. For this is 2.28. That's the maximum shear strain to fracture increases with the normal compressive stress. And for this reason, small or negative reading angles will often be used to machine less volatile material in order to promote shearing without fracture. So can you write down here? So for the brittle material, we use negative reading angle. Why? Because for the brittle material, if we have the compressive stress, and we can prevent our workpiece from fracturing, from cracking. Right now. So I have several papers talking about whenever we want to machine this is the brittle material, and one way is that we use negative tool, a tool with negative rectangle. The reason is that if we use negative rectangle, okay, so say this is my tool with a workpiece, is a negative rectangle. If this is the case, my tool will compress the workpiece. So can prevent the cracks from initiating and the crack propagating. However, if for the brittle material, the fracture toughness is low, right? So if I use the tool that has positive rectangle, that means if I use the sharp tool, I have a tensile, right? Tensile stress to the workpiece. That is the brittle material will be much easier to fracture. Write down. Okay, so this is the observation, and you need to know that. So this effect, I want you to know maybe in our midterm exam or as a part of the homework. I ask you should know that. So here is the shear stress distribution on the tool face. And suppose this is a tool and this is a flank face. So this is a rig face. This is a rig face. You can see the flank face. And so we have the tool. Okay, the chip is working, is flowing on this rig face. The chip is generating, and it is flowing on the workpiece. So we have two regions. One is called staking, and staking means that the stress will be very, very high. So this is very, very high. Another one is called sliding. Another area is called sliding. And here, so the chip will be separating from the tool face. So here is a distribution of normal and shear stress. Normal and shear stress. This is the sigma. This is shear stress, normal stress, and so this is the tau. This is shear stress. So we have two sigma and tau on the interface between the tool and the chip. So whereas the normal stress, see, normal stress increases continuously toward the tip of the tool. I know I told you. So this is the tip, tool tip. The shear stress reaches a maximum and remains at that value. So here is the shear stress is approximately the same for this area. So this is a phenomenon known as the staking. Staking means that the two objects come together. Right? So shear angle relationships. I can tell you all these. They are. This is empirical equation. They are not very accurate. If you want to get accurate, you need to do modeling or do the experiment. So here is the comparison of experimental and theoretical and shear angle relationship. More recent analytical studies have resulted in better agreement with experimental data. So this one, right? So here is a shear angle phi. So here is how to calculate this one, and they have used different equations and for different these materials, and they get different. This is you can get different the curves here. This is 820. 820, they calculate the phi using this equation. 45 degree plus alpha divided by 2 minus beta divided by 2. What is alpha, guys? I forget alpha. The rectangle, right? What is the beta? Huh? What is the beta? Huh? Clearance, right? Again? Relief angle, yeah, clearance angle. Okay, so alpha is a relief angle, the beta is a clearance angle or relief angle. Right? So these two angles both of them are for the tool. See? So they use this equation and to calculate the shear angle. Some people suffer and they use this one, it is modified. Definitely this one, they are different. But I will not say which one is better, right? So they just empirical estimation. So here, the B is the relationship between the shear angle and the friction angle for various alloys and cutting speed. So this is phi equals alpha. Phi equals alpha if alpha is greater than 15, and phi equals 15 if alpha is less than 15. This is it's not accurate. But if we have a new material and we can just at least using one of these material equations to get some estimation, right? Questions so far? So specific energy. So whenever we talk about specific something, and what comes into your mind? I would say specific energy, specific heat, or specific something else. What comes into your mind? Huh? Mass or volume? Oh, okay. But we we talk about species, we talk about the volume. Volume and mass is the same, right? So density, because we just assume the density is constant. That won't change. Yes, okay. Good. So species energy means that the energy, specific energy. See, specific energy requirements in machining operation. So for aluminum alloy, so you need to use these to remove the material. So from the perspective of energy, if we want to remove some layers off from the raw material, actually you need to provide some energy, right? So here, so you need to check this table. So this table is also estimate. It's not very accurate. But some people have already done this one for us and give you some basic idea. That's great. So the energy, okay? So the energy is required. The energy is applied in terms of the cutting force. In terms of force, you apply to the tool. So cast iron is a little bit higher, copper higher. And you can see titanium alloys is much higher, right? So we know if you for the same amount of material, and we will need much more energy when we machine this guy than for this than we machine the aluminum alloy. This is understandable. Right, everyone? So material removal rate. We will talk about the material removal rate. So the machining is also called material removal, the processes. So and here two columns. One is written in the English unit, in the standard. I'm sorry. So the international unit, and so this one is written in the English unit. Any questions so far? Everyone, any questions? No question? Are you confused? Are you question?
Back to the dynamometer that you're talking about, that just like measures torque and stuff, right?
Dynamometer?
Yeah.
Dynamometer is used to measure the cutting forces.
Cutting forces?
Yeah.
Okay.
How much force you apply in three directions? X, Y, Z, three directions. Dynamometer. So FC and FT can be directly recorded. However, F is a shear force and normal force, they cannot. What? So any questions regarding our homework 4, the advanced FEM modeling? No? Question?
How long should it take to do the whole work?
How long?
Yeah.
That's a good question. Depends on the
You don't
computer.
wanna know.
Huh?
We got to MDH at 5 p.m. We left at 2 a.m.
Takes about 6 hours to run the simulation.
Yes.
Okay. Can you just submit it and log it leave? You?
But do you really want to leave your flash drive there?
No, don't leave your flash drive there, but you can just save temporarily on the local drive.
They delete like clear
They
little
wipe
They're
out.
in the middle of wiping.
Yeah, they're wiping all of the computers right now, so you can't save locally. It's like he has to reformat.
Yeah, so just take the rest of it.
You cannot save locally now.
Yeah, for like the next week or two.
Yeah, they got a message written on the label.
IPS has, is just doing something.
Okay, let me talk to them. What that does now. So ideally, after you submit your simulation and you log it and read some signs say some simulations are being running, please don't touch. Well, thank you. Remember say as the last word, say thank you very much. And I will talk with IPS. Okay?